Hello everyone. So today we are going to start a new topic, and that is waves and oscillation. Now what do you understand by waves? We are not talking about the waves that we see in our ocean or some sort of big water bodies. Yeah, they have some similarities, and we will be taking that for an example to study waves. But before we start to understand what is wave, we have to understand what is oscillation at first. So the definition for oscillation is very simple. When any object, it can be any kind of object, when any object retraces the same path again and again. So let's say something is rotating around an axis. So it is covering the same and same path again and again. So when somebody will, what you say, like retrace the same path again and again, that we can called an oscillation. So oscillation can be like this even. An oscillation can be like what you say, if somebody goes like this and again this. So if it is going like this and then coming back and then again going, so if it is oscillating like this, then also this is oscillation. Now some of the examples I will be giving about oscillation. So let us take example of many situations. So the first situation what we will be having, let's say we have a spring here, we have a block, a mass here, and I disturb the mass somehow. Sorry, I disturb the mass somehow. So what will happen if I just pull it and just leave it? So this mass will go back and forth again and again. This back and forth motion is called as oscillation. So this oscillation that is happening, it's linear. That means it is retracing the same path again and again, and the path is linear. Let's say the another example is I have a stone and I am moving the stone like this way. So that means the stone is rotating with this rope. The rope is producing some tension towards the stone, and this is the axis in the middle, and this is retracing the same path again and again. So it's a circular motion, and that is an oscillation. One more thing is there, like let's say we have a pendulum here. So we have a mass here at the bottom, and with the help of a thread, the mass is hanging. Now if I disturb this little bit, so what will happen? It will go up to certain extent. This is the force of tension, which is restricting the mass to tear off and fall down. So if I just lift this mass up to this point, so what will happen? Then when I will drop it, it will go like this, and again it will come like this. So this motion will again keep on going in this zigzag way, and that is also oscillation. Now these things are called oscillations. Now there is something which is called SHM, simple harmonic oscillation. Harmonic oscillation. Now I say that the definition of oscillation is very simple. If something retraces same path again and again, it's oscillation. But simple harmonic oscillation is a special kind of oscillation where it will retrace the same path in the same time period. Okay, so let's say I have a what you say, that stone here, and the stone is rotating in a circular path. Now if this rotation, like the stone is going and then coming back, if this thing is happening in t time, So every time it is completing the rotation in t time, so then I can say that yes, this oscillation is simple harmonic oscillation. One more thing is there in case of simple harmonic oscillation. One more condition is there, but this condition we will try to understand with our spring law. So we know that the spring will always, like if I want to pull this object, the spring will not be very happy to be extend, right, to be elongated. So what the spring will do, the spring will give another force in the opposite direction, and the force will be F equal to minus kx, right. This is the restoring force to retain its shape. So the spring want to reserve its shape. It does not want to change its shape, so that's why it will give you opposite force. So one thing you can see that if I just pull this thing, if I just pull the bob or this mass and then I leave it, what will happen? It will come and go like this, right? So it will go and come like this, it will happen. So this is the point of equilibrium, and this point is the extreme point when the spring will be elongated like this, and this one is the compression point. So this is the, like when the spring will be compressed, right. So and medium one, like the middle one is the equilibrium point. So equilibrium point is that point when everything will be in equilibrium, there will be no force on the bob itself. Now one thing you see here, that when the bob is going in this direction, the force is always working in opposite direction. So the acceleration of the bob is also working in opposite direction. Again, when the bob is going in this direction, the spring does not want to compress. So what it will do, it will give force in opposite direction. So the acceleration of the body will be also in opposite direction. So you can see that the acceleration is always towards the equilibrium point. So in simple harmonic oscillation, this is a very important condition, that the acceleration of the body, the acceleration will be towards the equilibrium point. Equilibrium point. And one more thing is there, that the time period is same in this case. The time period will be constant. Now we know about oscillations, so we will be talking about how to study oscillations. Okay, so what we need to study oscillation. So we can take any kind of example, but I will take both of the examples so that it will be very much clear to you. Let's say here something is rotating with some axis. Okay, so this is rotating like this, and here I have a pendulum, which this is the equilibrium point, and the pendulum is going like this and that. Okay, so it is going like this and that. So this pendulum one you can see in the clock, the old grandfather's clock. Okay, so now in case of oscillations, I told you that time period is the time to complete one full oscillation. So time period for this event and time period for this event is the time taken for one complete oscillation. So one thing you can see, that in this kind of scenario where you can have the spring one, so you can see that in all of the cases, though oscillation is happening, but what will be that parameter which you want to study the oscillation. So there is no such thing. Like in the case of circle, we have to then measure the arc length, and that will be not be easy. And then we have for this pendulum motion, we have to measure this kind of arc length or this length, and that will also not be very much easy. Okay. And for our this motion, even back and forth motion for spring, then we have to measure the distance from here. So in all of the cases, different things we need. So to solve this problem, what we have done, so the physicist has thought about it, and they have found out one very nice idea. They have introduced the parameter of angle to measure the oscillation. So when this bob will complete one complete oscillation, we will say that this has covered the angle equal to 2 pi. So 2 pi angle covered means it has completed one full oscillation. Okay. In case of this, we will say also 2 pi will be the what you say. So this angle is called actually phase. Okay, phase. This angle is called phase. So the phase is a parameter to measure the oscillation. Okay, that means to study the oscillation. So in case of this pendulum, when let's say this is A point, B point, and C point. So when the pendulum will be at A, so I will say that 2 pi phase it will cover when it will go from A to B and then C, and then it will again return from C to B, then A. So from A it will leave, and then again it will come to at A. So when it will come to the same initial point from where it has started, we will say that it has covered 2 pi phase. So this angle is not physical angle that you can measure from here or here. This is not the physical angle, but this angle is the angle which we have considered for our calculation. Okay, to study oscillation. So all of the oscillations we can study using phase. Okay, so in this case also, when this mass is going back and forth, so when let's say I'm just drawing downside, let's say this is the equilibrium point at like say O, and this is my A and this is B. So again, let's say it has started from B, so I have pulled till B and then I just left it. So it will come to A and again it will return to B. So when it will return to B, that means the initial position, we will say that it has covered 2 pi phase. So this is the parameter we will be using to understand about oscillation. Okay. So because we are introducing phase here, which is an angle, so the next thing which I want to know is how fast the oscillation is happening. Okay, so how fast it is completing the same path again and again, how fast it is coming to the initial state again and again, that I need to understand. That means I need something which is related to speed or something like that. So because it is an angle, so I cannot use the concept of speed here, because speed cannot be dealt with angle. So what I need, I will be remembering my old classes when we were studying about angular motion, and sorry, and in case of angular motion we have seen that our whenever the angle is coming, to measure how much the phase is changing or how much the angle is changing with respect to time, we use angular velocity. So here also we use angular velocity. Sorry, angular velocity, and this angular velocity will be taking again as W or omega. This is called omega actually. So angular velocity will be that what is the rate of change of phase with respect to time. So the total phase, let's say if the total phase, so I know that that a complete oscillation requires t amount of time. So that means in t amount of time 2 pi phase will be covered, because I told you that in complete oscillation, like from initial state again coming to initial, the total phase covered we take as 2 pi. So that means in t time, so it's unitary method. So in t time it covers 2 pi phase. So in unit time it covers 2 pi by t. So that is called, in unit time, how much phase is being covered, that is called your angular velocity. Okay, so this is something we will be using for further. Now, how to understand the phases? Let's say I'm just taking one small example at first. So let's say this, again, that stone is rotating with same angular velocity, so that it is covering the same path again and again in the same time. Okay, so if the total time it is taking is t, then the time taken for this for this stone to come from A to B will be t by 2. That is for sure, if t is the total time. And similarly, the time taken for this mass or stone to come from A to C will be t by 4. So if I talk about what will be then if the ball is coming from A to D, so that means it is covering t by 4, t by 4 and t by 4. So that will be in total 3t by 4 time. So one thing you see here, we can do the similar approach to our phase also. I say that if it is going from A and again it is coming to A, the total phase is 2 pi. So that means if it is coming from A to B, the phase will be pi. That means 2 pi by 2. So if it is coming from A to C, the phase will be pi by 2, right? Pi by 2. More half we have to do. So each of this quarter will be pi by 2, pi by 2, pi by 2, like that. Okay. So accordingly, we can write some sort of graph even. Okay. So where I can show you that how the phase is changing. So let's say it has started from A point. Okay. So what will happen? So in this way, we are just let's say time is being shown here, or phase is being shown here. So what is happening actually? Let us understand first. So as the time is increasing, so the phase is also increasing. So first, let's say okay, wait. Let me tell you something. Okay. So at first the phi is increasing, right? So first it will go to pi by 2, like that, and then time will increase, so this will increase also. But to understand this thing, we can take help of our trigonometry. Now how we will take care of our trigonometry? So in case of this kind of oscillation, this is for a circle, but if we understand if we take help of our shadow technique, then it will be very much clear. How? Let's say I am taking one reference along this line. Okay, along this line I am taking one reference. Now the stone was there in A point. Now suddenly the stone has come to this point. Okay, this point. So if I want to measure the displacement covered by the stone, then I have to measure like let's say I am giving a torchlight here, and the shadow will form here, right? The shadow of this bob will form here. So I want to measure this part. So this part I can measure using say, let's say this angle is something, let's say phi, I don't know. Okay, this can be pi by, like we have pi by 2, like that. Phi can have any value. Let's say phi can be let's say pi by 4, even pi by 4 pi can be. Okay, so just like that, phi is the value of the phase here, let's say. So if this is phi, then this will be phi as well. So this part, the opposite part, will be sine phi component, right? So if this total hypotenuse is y, then this will be, sorry, a, let's say a, this hypotenuse is a, let's say the radius is a here. So this will be a sine theta, right? So if you can see here that this a sine phi will be maximum when this stone will come here, because when the, so this is a sine phi. This is little bit tricky and little bit confusing. It will, yeah, like gradually you will understand. Okay, so when this stone will come at C, the angle covered will be pi by 2. So you know that sine pi by 2 is 1. That means the displacement, this is another parameter which I am taking just to draw some sort of graph. So this displacement will be then the maximum. So y max will be a, because sine pi by 2 is 1. And it will be minimum when this stone will be at A or at B, because in those cases either the angle will be 0 or the angle will be 180 degree, that is pi. So sine pi or sine 0, both are 0. So y minimum will be 0. So you can see here that y is a sine function now. So with time, so time is increasing. So what will happen to my y function here? To understand oscillation, we can draw something like this. Something like this we can draw. So that means the value of y will be maximum when your what to say, when your this sine phi will be pi by 2. So this part here we have pi by 2. So that means when the graph is coming from this point to this point, it is covering a phase of pi by 2. Okay. So this is just a mathematical expressions. Okay, there is no physicality. We have created this just to understand the oscillation. That's it. Okay. Now let us do this thing with our pendulum. Okay, so that you can understand better. Let's say we have a pendulum right here, and the pendulum is oscillating like this. So this is the L, is the length of the pendulum. So you can see here that the radius, this L is same everywhere, right? With time the L will not change. What will change? The phi, that phase will change. Okay, so phi will change, the time will change obviously, and something we need that has to be changed also. So that parameter is your displacement. So what we do, we take this, we take a shadow again. So here we can put a dot, and we can say that this displacement is again the maximum value of amplitude. Okay, so okay, one more thing I have not told you. So the extreme corner, let's say this is the equilibrium point, right? So we know that this is the equilibrium point. That means if I just leave it here, it will not move at all. And the extreme point, these two extreme points, if I pull the bob to the extreme points, this length will be called as amplitude. Okay, so this length is called as amplitude. Okay, so this amplitude, so we have taken another parameter, that is y, which is amplitude into sine phi. Okay, so what is this y here? So you can look here and you can just try to understand what is y here. So we can see here that in case of this pendulum, if we take this triangle, we know that this phi can be any kind of phase value, but here you cannot show that this is the theta, so this is the phi. This you cannot do. Okay, so phi, this phi and this theta is not the same thing. That I want to make you understand. This phi is the angle or the phase that we have taken just for our calculation. Okay, so when let's say this is A point, let me use different color. Let's say this is A point, this is B point, this is C point. When the bob will be at A, the phi will be 0. When the bob will come to B, that is from here it has come to equilibrium point. So how many steps are here? We have to measure. Okay, that will be easy. So first it will come to here, that means 1 step. Again it will come to here, 2 step. Again it will come to here, 3 step, and then again it will come to initial position, 4 step. So in each of the step, the whole step is 2 pi. So each of the step will be only pi by 4. So that means, sorry, pi by 2. So that means from A to B, so when the bob will come to B position, the value of phi will be pi by 2. So I'm just writing it here so that you can understand. So the value of pi will be, so at A the phi will be 0, at B the phi will be pi by 2, at C the phi will be another pi by 2, that is pi, and then at D the phi will be again 2 pi. Okay, 2 pi. So this is the situation with phi and this angle theta. So I'm telling you that this phi is just for our calculation. This we take just for calculation. And this y even is the displacement that we also take just for calculation. Okay. Okay, this is the general form of any sort of oscillation. So any kind of oscillation we can express in terms of this. So what is this y? This y is the displacement from the position of equilibrium point for any such kind of value of phi. So this we can understand very easily with the help of the spring one. So let's say this is the spring one. So this was the equilibrium point 0, and if I pull it till this much, so that will be my extreme points, that is, let's say A. So this amplitude is A here. So if I leave it, it will again go and compress in this part. So this is the B point. So this is even A. Fine. So let's say I want to find out that when this phi is some value, any value, let me say, I know that from this A, when it comes to O, it covers only pi by 2. But let's say I want to know where it would be when the value will be pi by 4. So then this equation will come to play the role. Then y will be equal to A, that is this amplitude, into sine pi by 4. So what it will come? It will come A by root 2, right? So that means from this 0 point, the position of the bob will be at A by root 2 distance. So this is the displacement which is connecting our theoretical or our abstract parameter phi with our real parameter y. Okay, so this y is the displacement from the equilibrium point. So in this case also we can say that this y here is the displacement of our bob when, so you know that bob will not come in this way. The bob will go like this way and that way, right? But the shadow of bob, you can say, will come. So when the bob is here, the shadow of bob is here. So this we can find out. So this distance is our y, which we can find out. So for different equation we can, for different situation we can use the same formula, that is y equal to sine phi. Okay, so I know that this is a little bit what you say, confusing. It will take time to understand, and so this is the basic thing. If phi, what we take to study oscillation, is abstract, but this y is the real thing which we can measure, and with this equation there is a connection between our abstract thinking and the realism. Okay. Now one more topic is there, that is called frequency, and we will be looking back into this equation one more time. So what is frequency? Frequency is a very easy concept. So let's say something is rotating. Okay, something is rotating. So I know that in t time it rotates one revolution, right? So in t times it completes one rotation. So let's say in t time it completes one revolution. So in one time it completes how much revolution? So let's say in 1 second. In 1 second it completes 1 by t revolution. So that is called the frequency, f. So f is your 1 by t. This is called your linear frequency. We'll come to angular frequency in the next class. So linear frequency is the number of oscillation that is occurring in 1 second. So you have high-speed fans, propellers you have seen, the vehicles, wheels you have seen, which rotates. So obviously they rotates they rotates for lots of revolution in unit time, right? Some where you have seen that in 1 second it rotates for 100 revolution or 200 revolution. So the unit of this thing is also very easy. In SI unit we say it is hertz, Hz. So hertz means, like, if you have 55 hertz, that means in 1 second it rotates 55 times. So some also uses the RPM, that is revolution per minute. So in 1 minute how much revolution is occurring. If you find out instead of this 1 second you are finding, let's say you are finding out for minute, per minute, so that will be your RPM. Okay. So this is the concept of frequency, right? So what we can get from this, so I have seen that omega is equal to 2 pi by t, whereas in the last topic we have seen that 1 by t is the frequency. So we can relate frequency with our angular velocity and this angular speed. Okay, so this angular speed is what? How much the phase of the system which we have imagined, how much the phase of the system is changing. Okay, that is fine. And one more thing that you can see here, this omega is equal to 2 pi by t. That means omega is the angle, that is the phase by time. So from here we can also write that a phase is equal to omega into t, right? So this t is the time required to create phi phase, right? That means to cover phi angle. Okay, so this equation we can even rewrite a sine phi. This was the equation for our oscillation. Okay, so this we can recreate, and we can write y equal to a sine omega t, and this is the final thing we are getting. So if we draw this graph in the next page, what we will get, let's say this is the graph. So here we have y and here we have time. This is the initial position from where it's starting. So the equation you write at first, that is a sine omega t. So you have seen that when the time is t, okay, so at t is equal to 0, it will be at initial position. But when the time will be t, big T, that is a complete oscillation. So what will happen to this y? This y will go to the maximum, right? So from 0, it is reaching up to, like, it will go like this and it will come like this, again it will go like this and come like this. Now we have to find out the oscillation. So you have seen it is the initial position, let's say. Okay, let's say we are talking about a spring motion. So this is the equivalent position, and this is the extreme position. Okay, and this is this extreme position, and the amplitude is, so one thing you can say, this is plus a amplitude and this is minus a amplitude, because it is going in the left side. So the maximum is the maximum height is a plus a, and the minimum, so here will be minus a, right? So how to level the time? So I have told you that it has 4 steps. It will come, it will go, it will again come here, and it will come into initial position. So for a total one, so 4 steps are there. Total revolution, a complete rotation is taking total t time. So that means each quarter is taking t by 4 time. So that means this is t by 4, this is t by 2, this is again your 3t by 4, and this is 4t by 4, that is t, and so on it will go. Okay, so that means when the time period is this one, this full thing, this complete curve will be your complete oscillation. Okay, so this full going and coming means a complete oscillation. Okay, so the phase even we can give here, label here. So this is the phase, so you can put the value of time in this formula and we can find out the phase easily. We know that omega is 2 pi f. Now right now we have seen, and also we know that omega is 2 pi by t, so we can use this. So I can write this y equal to a sine omega, instead of omega I can write 2 pi by t, and then this small t. So if I put this t by 4, matlab t by 4 in t by 4 time, if I want to know what is the value of phase here, how much angle it has covered, so I will put here t by 4. So t will cut, this will cut, I will get sine pi by 2. So your y will be a. So I am getting here the same result. Y is the a at t by 4. So it is matching. Again, let's say I am just trying to put any other value. Let's say I am trying to put this value t by 2. So I'll put 2 pi by big T into t by 2. So t will cut, 2 will cut, sine pi. So sine pi means how much? It's 0. And you can see here that the displacement is 0 at t by 2. So that means it is again matching. So this is the way we study oscillation. Okay, and you have to understand the the concept of phase and why we need it. We need it just to study the all kind of oscillation under the same umbrella. Okay, so this much is there for today. We will be talking more about it in the next class, and then we will study about waves. So bye bye, take care.